The equilibrium position is going to represent the lowest free energy value available to a reaction system. Right? The free energy is dependent on the pressure of a gas or on the concentration of a species of solution, and thus its value changes as the reaction proceeds. So, reactions are almost always in something other than their standard states. Right? When are you going to find something that is 1 molar? Right? All the things are 1 molar, and they're going to stay that way. So as soon as that reaction happens, some of your product's getting consumed, or reactants are getting made, or it's going the other way. Your concentrations change. So very, very rarely will things be in their actual standard states. Our free energy is needed to determine if reaction is spontaneous or not. And how does the free energy change when you change things like concentration? So here is another absolutely beautiful equation coming up. Right? Our delta G, right, so our plain old ordinary delta G here is going to be related to the standard state delta G's that you would get from your tables, right? You just do some tables, and you're going to do, right, the sum of the delta G's of the products minus the sum of the delta G naughts, the reactants, right? So, but you're going to need to adjust it to get your non-standard state free energy. And you're going to need to account for things like temperature and the ideal gas law to make it all work. And it's going to be adjusted in some kind of natural log kind of way, right? Because our entropy is really going to be natural log based. And ln of Q, right? That's just our good old friend products over reactants, reaction quotient Q, right? It's that same Q. So what we're doing now is we're tying together our free energy and our equilibrium. So this is really saying why do things happen the way they happen way back in chapter 12? It's because of their free energy. This is what is happening and why you're doing it. So we get our standard state free energy from our tables. We get our delta. We get our R from 8.314 joules per mole Kelvin. Our T is our temperature in Kelvin, and Q, that's our reaction quotient. So we can do something like calculate the free energy under non-standard conditions. So for our Haber synthesis of ammonia, right, this is our balanced chemical equation. We're going to take nitrogen gas and hydrogen gas, and we're going to form some ammonia. Right? And our Q is going to be the partial pressure of the ammonia squared divided by the partial pressure of the nitrogen and the partial pressure of the hydrogen cubed. Right? So we want to calculate delta. All right, so once we know what those values are, we can go ahead and solve for our delta G under those non-standard conditions, right? Just got to solve what Q is. We got to then use that to adjust the values we look up from the table by a certain amount. So let's do an example. We're going to calculate delta G under non-standard conditions for the formation of ethylene from carbon and hydrogen gas when the partial pressures are 100 atmospheres of H2 and 0.1 atmospheres of ethylene. Our delta G naught, if we looked it up on the table and did that products minus the delta G of the reactants, we'd end up with positive 68.1 kilojoules. So for our reaction where our carbon is reacting with the hydrogen to form the ethylene, right, we're going to use our equation delta G is equal to delta G naught plus RT ln Q. Right? We already have the delta G naught. We calculated that up before. And we're going to do RT ln of Q as products over reactants. So we'll get 68.1 kilojoules plus 8.314 joules per mole Kelvin times 298 Kelvin. And then we're going to do the natural log of our products over our reactants, keeping in mind that this guy is going to be H2 squared. Carbon doesn't show up in our K because it's solid. I've got some numbers I can plug in. We're going to get 68.1 plus negative 28.5, and we get 39.4 kilojoules. So under these reaction conditions, because delta G is positive 39.47, it's positive delta G, it's non-spontaneous. Delta G needs to be negative. So, sorry, giant typo there. All right, what is the delta G for a reaction where you've got 2A gas going to 3B gas at 303 Kelvin if delta G naught is 8.7 kilojoules per mole and the initial pressures are going to be 0.534 atmospheres and the partial pressure of B is 0.274 atmospheres? All right, the answer is going to be C. So here's the next neat little trick, is that we've got the equation delta G is equal to our standard state delta G, and we're adjusting it by some RT ln Q. But at equilibrium, we know that this delta G term here is going to be equal to 0, and Q is going to be equal to K. So delta G naught, those things we look up under our standard state conditions off of the table, is going to be equal to minus RT ln K. And that's just beautiful, because now we've got this direct connection between energy and our equilibria, and we can see how it ties into temperature and why sometimes at different temperatures we're going to have a temperature dependence on K, because we're going to have an energy dependence on K. And part of why we're going to have those things connected to each other has to do with those activation energies that are dealing with the kinetics. So if delta G naught is less than 0, our ln of K is going to be bigger than 0. So K is going to be bigger than 0. So it's going to be mainly products. If delta G is less than, delta G naught is bigger than 0, ln of K is going to be less than 0. K is going to be less than 1. It's going to be mainly reactants. And if delta G naught is equal to 0, K is equal to 0, and it's 1, it's going to be a mixture. Right? And so we're tying our delta G and our K together. Right? So what is the meaning of delta G for a chemical reaction? A system can achieve the lowest possible free energy by going to equilibrium and not by going to completion. Right? So that's why you're not going to see A goes to B, right? And we're going to have no A left over, right? And that's why you're never ever going to get a percent yield equal to 100. It's never going to be 100% yield, because you're going to achieve that lowest possible free energy by going to equilibrium, not necessarily to completion. Delta G predicts whether we're going to go towards the products or whether we're going to go towards the reactants the same way Q does, because Q is really just a representation of K. And it does not mean that the system will proceed to pure products if delta G is negative, or that it will remain at pure reactants if delta G is positive. And it's saying that the system will spontaneously go towards that equilibrium position, the lowest possible free energy available to it. Right? So here's an example, a schematic representation of what's happening energetically. So, if you're moving this ball down the hill, right, you're striving to find the lowest possible gravitational potential energy. And that's what rolling a ball down the hill spontaneously happens, right? So if I've got, instead of a ball, and I label this, R for reactants, and over here as P for products. As I'm rolling this ball down the hill, up here, Q is going to be bigger than K. So let's take a look at this ball rolling down a hill. That ball rolling down the hill, this is the spontaneous process. You're changing out one higher gravitational potential energy for a lower potential energy. And what we're going to see with our representation here is, what if I call this side, say, the reactants, and this side over here, the products? Well, if I'm starting up here and I'm rolling down towards this equilibrium position C, my lowest possible energy state, right? I've got a Q, and then it's going to be less than K. Well, if I had this ball and it's got a lot of energy, right, it's going to roll up a little bit on the product side, make too much products. Well, now Q is going to be bigger then K, and that ball's going to roll back down the hill. And what will happen to this ball over time? All right, it's going to go up and down and up and down and up and down. It's going to roll up and down and up and down until it eventually stabilizes out at that equilibrium position, that lowest possible energy. Right? No more work is able to be done. The equilibrium point occurs at the lowest value of free energy, right, where we can't do any more work. So when substances undergo a chemical reaction, the reaction proceeds to the minimum free energy, equilibrium, which corresponds to a point where the energy of the products is equal to the energy of the reactants, or we could say that the energy of the products minus the energy of the reactants is 0. So where delta G is equal to 0. At equilibrium, delta G is equal to 0, and Q is equal to K. So we can take this and rearrange the equation we had before and say delta G naught is equal to minus RT ln K. And that's really just amazing and beautiful. Give yourself a little smiley face next to that or something. All right? So this is just that same thing we saw before. So if we're looking up with G as being our energy and we're looking at a fraction of A being reacted, in A, the free energy changed to reach equilibrium beginning with 1 mole of A and 2 moles of gas. We're going to start moving forward. Right? In B, the change in free energy to reach equilibrium beginning with 1 mole of B, our product. Right? It's going to roll down the hill backwards. So if we start off with just product, it's going to roll backwards to reach equilibrium. If we start off with just reactant, it's going to roll forwards. Right? And so that our fraction of A reacted is going to reach some stable point that's at equilibrium. And so our free energy profile for a reaction of A going to B containing 1 mole of gas, A and B, right, is going to reach that minimum point, where the P total is actually going to be 2 ATM. Right? And that's going to correspond to the total free energy of a combination of A and B. Right? This table here just summarizes that relationship between G naught and K. Looking at another example, the overall reaction for the corrosion or rusting of iron by oxygen is that we're going to take some iron solid and react it with some oxygen gas to form Fe2O3. Using the following data, calculate the equilibrium constant for this reaction at 25 degrees C. Well, we already know something about the enthalpies, right? Those guys are going to be 0. Our entropies are always going to be some number. We're always going to have a number. Our standard state entropies are going to be positive. They're going to always have something. Doesn't matter whether you're in a pure substance or not. So if we've got this, can we calculate a value for G? Right? And if we've got a value for G, can we then calculate the value for K? And that's what we're going to do. So we're going to use our H minus T delta S to find G, and from G we're going to find K. So to calculate the K, we're going to use the equation delta G naught is equal to delta H naught minus T delta S naught. So we're going to calculate delta G and say that that's going to be equal to minus RT ln K. Because delta G is the same delta G, we can rearrange those two equations and combine them and say that delta H naught minus T delta S is equal to minus RT ln K. So we're going to do our delta H, right? We're going to find those delta H's. All right, we're going to do 2 times the enthalpy of formation for the iron minus 3 times the enthalpy of formation for the water. Minus 4 times the enthalpy of formation of the iron solid. So we're going to get 2 moles times minus 268 minus 0 plus 0 is going to give you minus 1,652 kilojoules, or 1.6 minus 1.65 times 10 to the 6th joules. That's our delta H. Our delta S, we're going to do the same, adding up the sum of our standard state entropies of our products minus our standard state entropies for our reactants. So we're going to do 2 moles times 90 minus 3 moles times 205 minus 4 moles times 227, and we end up with negative 543 joules per Kelvin. Our temperature, we're going to convert that into Kelvin, because we're always going to need to do this in Kelvin. So our delta G is going to be delta H minus T delta S. All right, we just got our temperature in Kelvin. We just got our delta S. We got our delta H from the other page. So our overall delta G is going to be minus 1.4 kilojoules or 1.5 kilojoules. Once we've got this, delta G, we just did that, we're going to use our minus RT ln K. So we know that minus RT ln K is minus 1.5 kilojoules. So when we do minus, we plug in our value for R, we'll plug in our value for T, we're going to solve for natural log of K. So we get natural log of K is going to be 1.5 times 10 to the 6th divided by 2.48 times 10 to the third, or 601. So we're going to do K is e to the 601, and that's a very, very large number. Right? So the rusting of iron is clearly very favorable from a thermodynamic standpoint. Can we calculate Kp from that reaction? That's what we're going to do for a reaction. Yeah, we're going to do that. So we've got calcium carbonate giving us calcium oxide and carbon dioxide gas. Our delta G is going to be equal to delta G naught plus RT ln Q. We're going to calculate delta G naught from our table. So we're going to do the sum of the products minus the sum of the reactants. So we got 1-to-1 stoichiometry, so 1 mole and minus 603.3 kilojoules per mole, and 1 mole times 394.4 kilojoules per mole. Then we're going to subtract the 1 mole times 1,129 kilojoules per mole, and we get a delta G of positive 131.4 kilojoules per mole. So we've got our balanced chemical equation. We now figured out delta G. All right, our delta G naught, we're going to put that in there. We know R, we know T. We're going to try to solve for ln of Q. At equilibrium, delta G is going to be equal to 0. So we're going to get 0 is equal to delta G naught plus RT ln K. So we're going to say 0 is equal to 134.4 kilojoules times R times T times ln of K. Notice that there is a bit of a unit mismatch because these guys are doing kilojoules and these guys are doing joules, so you're going to shove one to match. Right? And so we'll end up with minus 54.25 kilojoules is equal to ln of K. Do E as our exponent, natural log base E, to the minus 54 is going to be meaning that K is going to be 2.7 times 10 to the minus 24, so it's not very stable. It's not very thermodynamically favored. It's not going to favor the products. All right, so you're going to take calcium carbonate, you're going to take calcium oxide and react it with carbon dioxide to form calcium carbonate, and that's that lime scale gross stuff that you see like collecting on your pipes. I mean, if you got hard water, and you can remove that by using just some vinegar, right? Acidify it. So let's consider this reaction. We're going to take H2 gas and chlorine gas, and we're going to make HCl, hydrochloric acid gas. How does the value of delta G change when the pressures of the gases are altered as follows at 25 degrees C? So if we've got 0.25 atmospheres of H2, 0.45 atmospheres of chlorine, and 0.3 atmospheres of HCl, what is our new value of delta G? All right, so we're going to use that same set of equations. So we got our balanced chemical equation. We're going to use our delta G naught. We're going to look up the values on the table. For the HCl, we're going to do 2 times the HCl's value minus 0 and 0, because these guys are elements in their natural state. So our delta G naught is going to be minus 190 kilojoules per mole. So that's kind of our starting position. We're going to calculate a Q, and that's going to be products over reactants. And we've put in our particular values. So we said it's 0.3 atmospheres squared, and then 0.25 times 0.45. So our value for Q is 0.8. So now we got a delta G naught. We got a Q. We're going to use our formula that says, all right, we're going to solve for delta G using delta G naught and RT ln Q. We knew our delta G naught. We got our R. We got our T. And then we've got our ln of 0.8. When we calculate it, we'll end up with minus 191 kilojoules per mole, and the reaction becomes more spontaneous. Our free energy is more negative. Let's look at another example. One method for synthesizing methanol involves reacting carbon monoxide and hydrogen gas. So CO gas and H2 gas gives us methanol, CH3OH. We're going to calculate the G at 25 degrees C for this reaction, where carbon monoxide gas at 5 atmospheres and hydrogen gases at 3 atmospheres are converted to liquid methanol. Right? Again, this is one of those ones where you kind of want to keep track of what that state is, for both K reasons and for delta G reasons. So to calculate delta G for this process, we're going to use our equation delta G is equal to delta G naught plus RT ln Q. So we're going to first compute the delta G naught from our standard enthalpy free energies of formation. So delta G of formation minus 166 kilojoules for the methanol. For hydrogen, it's 0 because it's an element in its natural state. And for our carbon monoxide, it's minus 137 kilojoules. So we're going to add those guys up, take their difference. So we're going to do products minus the reactants, and we end up with 29 kilojoules. Minus 29 kilojoules is our delta G naught. Note that this is the value for delta G naught for the reaction of 1 mole of carbon monoxide with 2 moles of H2 to produce 1 mole of methane. We might call this value delta G naught for 1 round of the reaction or for 1 mole's worth of the reaction. Thus, the delta G naught value might be better written as minus 2.9 times 10 to the 4 joules per mole of reaction, or minus 2.9 times 10 to the 4 joules per mole reaction. Right? So that's just another way to kind of think of this. We can now calculate delta G using the idea that delta G naught we've got from before. We just calculated that. We know our R. We know our temperature. We're going to calculate our Q. So we're going to have that 1 up there, remember, because that was a liquid. Partial pressure of the carbon monoxide, partial pressure of the hydrogen squared. That should be on the outside. So we're going to get 1 over 5.0 and times 3.0 squared. We're going to get 2.2 times 10 to the minus 2. So the pure liquid methanol is not included in that calculation of Q, just because that's what we do with our values for K. Put that into our expression for delta G naught plus RT ln Q. We've got our delta G naught value here. We've got our R. We got our R. We got our T. We got our Q. All right, we're going to do all of the math on that, just simplify it. So we're going to end up with minus 38 kilojoules per mole of reaction. Note that delta G is significantly more negative than delta G naught, implying that the reaction is more spontaneous at the reaction pressure is greater than 1 atmosphere, which is what you would expect from our good friend Le Chatelier. Right? The higher the pressure, right, you're going to shift that reaction.